So now we're going to do the problem. The step one, oh dear, it's not focused, is it? Step one for this problem is what we're going to write. Say this is equal to the real part of the integral from negative infinity to infinity e to the I z over z squared plus 1 dz. And this part wasn't really explained properly in the video, but these two integrals or sides of the equation are the same because this r, which is a real part symbol, you can bring that inside the integral, and if you take, and the denominator is real because we're integrating over the real line. The numerator, which is e to the I z, the real part of that is just cosine of z by Euler's identity. And then that would give us this. But it's still, like, if we didn't know you to do this, it's pretty strange idea. So from earlier, if we draw this as a picture, we have it an integral over the whole of the real line. But instead we could have it going from minus r to r, and let's just call this curve CR, and then what we're having is, we'll just concentrate on this, and then we'll take the real part afterwards, f of z for convenience. And then we'll do C of r, limit r goes to infinity of f of z dz. So this is what we want to find out. But for the moment, we'll forget the limit, and we're going to, so we've been inspired by Cauchy's residue theorem, or someone's residue, I forget, and we go around the loop like this. We can call this part gamma of r, and we have this point I, which is the residue. We have I and minus I residues, but minus I we can forget. We just need to concentrate on this I, and we want to know the residue of f of z. So we're not going to do the integral and work out the residue. We're going to work out the residue by, by inspection. So e to the iz, we can write this Taylor series out. So what we're doing right now is we want to work out the residue of f of z at 0. So we're trying to find out at I, residue at I. And to do that, we're going to first write down e to the iz as a Taylor series expansion, which is 1 plus iz plus iz squared and so on, plus dot 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 over 2 factorial, this is over 1 factorial, and so on. Okay, and then we have this, which we can use a geometric product thing to do. Don't forget the minus, because that's how it is. Now seeing this, I feel like maybe I've fudged up. Okay, the residue, the way you work it out, so if you have e to the iz over z squared plus 1, so we factorize this as z minus I z plus I. So what we want is the residue at z is I. So we cover up the z is I bit and we plug in I into the equation. This is so sus, I know, but and this gives us e to the minus 1 over 2i. So this is called the cover-up method. Okay, so that means the residue of I, we just got it, is 1 over 2i e in the most sus way. So that's something you need to remember for the exam, the cover-up method. Okay, so now you've got the residue. And like, why does the cover-up method work? Well, because if you go close to I, everything is approximated by this z minus I. Z minus I dominates over all the other terms, and so just covering up, then you get the actual dominant term, which is the residue. So we've got the residue, and then we'll continue this in the next episode because it's already gone so long.